Welcome back to Physics 191. I'm Gerard Blanchard, and last time we introduced the concept of momentum, conservation of momentum, and how to use it during collisions. Simply, whenever two objects collide or explode, which is a collision in reverse, the total momentum vector before the collision is equal to the total momentum vector after the collision. And remember that momentum is mass times velocity, and all of these are vectors. Momentum and velocity are vectors. So that gives us two equations. The total momentum in the x direction after the collision equals the total momentum in the x direction before the collision, and the total momentum in the y direction after the collision equals the total momentum in the y direction before the collision. So you have two equations there, an x equation and a y equation. So the idea, the physics concept that we apply to collisions or explosions is conservation momentum, which means that the total momentum of all the interacting objects before the collision equals the total momentum of all the interacting objects after the collision. So let's put that to work. Here's an exercise. 0.020 kilogram bullet traveling at 200 meters per second east hits a motionless 2 kilogram block and bounces off of it. Must be a rubber bullet. Retracing its original path with a velocity of 100 meters per second west. What is the final velocity of the block? Assume that the block rests on a perfectly frictionless horizontal surface. Please apply your momentum ideas and your momentum equation to this situation, and let's let you answer that question. Okay, we'll draw out the situation. Here's our bullet, and here's our block. The bullet is moving, the block is still. And afterwards, the bullet is moving back the way it came, and the block is moving. We'll call this X. The mass of the bullet, we'll call that mass 1, is 0.02, and that's sufficient, kilograms. The mass of the block, we'll call that mass 2, is 2 kilograms. V1 initial, or Vx1 initial, is 200 meters per second, and Vx2 initial is 0. That is our initial situation. Bullet moving at 200 meters per second in what we'll call east. That's the mass of the bullet, 0.02 kilograms. The block is initially not moving, and the block has a mass of 2 kilograms. Afterwards, the bullet is moving west, so we will write Vx2 final is minus 100 meters per second. Minus 100 meters per second because it is moving backwards relative to how it was before. And the block is moving with Vx2 final that we don't know and that we want to know. We use our idea where momentum in the x direction total initial equals momentum in the x direction total final. And I'll add that this is the initial situation and the final situation. So the total momentum in the x direction initially is the same as the total momentum in the x direction finally. So now it's a matter of adding everything up. Initially, we have 0.02 kilograms times 200 meters per second plus 0 for the block. And afterwards, we have 0.02 times negative 100 plus the mass of the block, which is 2, times Vx2 final. The only unknown there is V2x final. So let's see, 0.02 times 200 is 4 units of momentum before, and this would be minus 2 plus 2 Vx2 final. Well, I will add this 2 to both sides, and I will get 6 is equal to 2 Vx2 final. Or if I divide both sides by 2, then 3 is equal to Vx2 final. So finally, the block is moving at 3 meters per second in the positive x direction, or the direction that the bullet was moving initially. And so that's the answer to the question we were asked. Let's look at another exercise. Body A, which has a mass m, has an original velocity of 6 meters per second in the positive x direction towards a stationary body, body B, of the same mass. After the collision, body A has velocity components of 1 meter per second in the positive x direction and 2 meters per second in the positive y direction. What is the magnitude of body B's velocity after the collision? This is a two-dimensional collision, but we work it just the same as we do a one-dimensional collision. We just now have two equations, one for momentum in the x direction and one for momentum in the y direction. So, and notice that both bodies have the same mass, so we're going to be able to factor out mass, and it's not going to matter what the mass is. Try to answer this question. Okay, well, let's diagram the situation. Here is body A, and it has a velocity of 6 meters per second and a mass of m. And it collides with body B, which also has a mass of m and is initially at rest. And I will draw in my x and my y axes. This is our initial situation. Afterwards, body A is moving in the positive x direction and the positive y direction. So I will draw it like this. It's moving with 2 meters per second in the y direction and 1 meter per second in the x. So 1 in x, 2 in y. So it's moving like this. And body B, if body A is moving upwards, we'll assume that body B is moving downwards. So I will draw body B to be moving something like this, down and to the right. And so it has components V, B, X final and V, B, Y final. And what we're asked for is the magnitude V, B, which will be the hypotenuse, but we'll find that by finding V, B, X final and V, B, Y final. And this is our final situation. Okay, well, this is a collision. We use conservation of momentum, but we'll have to use conservation of momentum in the x direction and the y direction separately. So we have P total x final, P total x initial equals P total x final, and P total y initial equals P total y final. What do we have in the x direction? Well, initially we have mass m, whatever it is, moving at 6 meters per second in the x direction, so m times 6 equals P total x final. Well, body A has a mass of m, so in the end it's moving at 1 meter per second in the x, so that would be m times 1. And then body B also has a mass of m, so it'd be plus m times V, B, X final. Notice that everything is multiplied by m, so we can divide everything by m, and that will cancel out the m. We won't have to worry about that. And so we can see that VBX final is going to be 6 minus 1. So I'm going to subtract 1 from both sides. 6 minus 1 is equal to VBX final, or VBX final is equal to 5. So VBX final is 5 meters per second. And in the y direction, initially, we have nothing moving in the y direction. We're only moving in the x direction. So we have 0 in the y direction, 0 momentum in the y direction initially. Finally, we have mass m moving at positive 2 meters per second in y. So that would be m times 2. And then we have for mass B, or for block B, we have mass m plus mass m moving with a VBY final in the negative y direction. And negative y is different than a velocity in the negative y direction is different than a velocity in the positive y direction. So we have to write a negative sign for that. So negative VBY final. So that tells us that 0. And once again, we have mass everywhere. We have mass in every term. So we can divide by mass and cancel out the mass. So we have 2 minus VBX final is equal to 0, or VBY final by adding VBY final to both sides. VBY final is equal to 2. Now those are our components of VB. We have 5 meters per second in the positive x direction and 2 meters per second in the negative y direction. And so we want the magnitude of the velocity. We want the hypotenuse here. And so we would just take the square root of VBX final plus VBY final, or VB final is equal to VBX final squared plus VBY final squared, and take the square root, or VB final is equal to the square root of 5 squared plus 2 squared, or VB final is equal to the square root of 29, which is 5.39 meters per second. So that is the magnitude of velocities that's the magnitude of body B's velocity after the collision. And we've answered the question that was asked of us. Let's take a look at another exercise. A 1,500 kilogram car moving east at 17 meters per second collides with an 1,800 kilogram car moving south at 15 meters per second, and the two cars stick together. What is the velocity of the cars right after the collision? So we have two objects coming together from different directions, sticking together, and so they become one object, and we want to know what is their velocity right after the collision. Use your conservation momentum ideas and answer this question, please. Okay, let's draw our diagram as we always do. And once again, we'll have to use X and Y. And we'll make X be east and Y north. So we have a 1,500 kilogram car, 1500, a 1,500 kilogram car moving east. So it's moving in the positive X direction at 17 meters per second. And it collides with an 1,800 kilogram car moving south. So it's moving down. (1,800 kilograms moving south, moving down at 15 meters per second. So this is our initial situation. It's our initial situation. And they collide and stick together. So they become one big object, which has a mass of 1,500 plus 1,800 kilograms. And if the objects were initially moving south and east, then this mass we will assume will be moving southeast, so something like this. We could be wrong about that, but we'll assume that. And if we're wrong, then what will happen is that we will get a negative sign for one of our components, but I don't think we will. So we have V, and I'll call that, I'll just call that V X final and V Y final. And then the hypotenuse will be V final. So this is our final situation. This is our initial situation, our final situation. And as always, we're going to use conservation of momentum, which tells us that P total X initial equals P total X final, and P total Y initial equals P total Y final. The initial momentum in the X direction comes from the 1,500 kilogram car, so that would be 1,500 times 17. And finally, we have the combined object, 1,500 plus 1,800, moving with V X final. And in the Y direction, we have 1,800 kilograms moving with negative 15 meters per second, and that is equal to 1,500 plus 1,800. And our Vy final, we're assuming, is going to be in the negative Y direction, so minus Vy final. And in each of these equations, we only have one unknown, so we can solve for 1,500 times 17 divided by 1,500 plus 1,800 is equal to Vx final, which is 1,500 times 17 divided by 1,500 plus 1,800, and that would be 7.73 meters per second. Is Vx final. And over here in the Y direction, we would have 1,800 times negative 15 divided by 1,500 plus 1,800 is equal to negative Vy final. There's a negative sign right there. Negative Vy final. And so I'll also multiply both sides by negative 1, which will cancel out that negative sign right there. And we have 1,800 times 15 divided by 1,500 plus 1,800. And that would give us 8.18 meters per second as our Vy final. So after the collision, the object is moving 7.73 meters per second in the x direction and 8.18 meters per second in the negative y direction. We could also represent that as the magnitude and the direction. And so we would have to calculate the magnitude, which would be V final is equal to the square root of Vx final squared plus Vy final squared. And so that would be V final is equal to the square root of 7.73 squared plus 8.18 squared, which gives us a V final of 7.73 squared, square root of 7.73 squared plus 8.18 squared, 11.3 meters per second. And the angle, which we'll call theta, is going to be the inverse tangent of the opposite over the adjacent, or so theta is equal to the inverse tangent of Vy final over Vx final. Theta is the inverse tangent of 8.18 divided by 7.73, or theta is equal to the inverse tangent of 8.18 divided by 7.73, and that gives us 46.6 degrees. And we have to note that it is 46.6 degrees south of east. This would be east, and it is south of east. So that would be 46.6 degrees south of east, or 46.6 degrees below the x-axis. So that answers the question we were asked. We could say that the velocity of the combined wreckage is 7.73 meters per second in the x direction and 8.18 meters per second in the negative y direction. Or we could say that they have a speed of 11.3 meters per second in the direction of 46.6 degrees south of east. So that answers the question that we were asked. Once again, we answered it using conservation of momentum. Total momentum in the x direction initially equals total momentum in the x direction finally. Total momentum in the y direction initially is equal to the total momentum in the y direction finally. Now, so far, you have been told that either the objects collided and stuck together, or you've been given the velocity of one of the objects after the collision. Well, using something called the coefficient of restitution between the objects, we can solve for questions where you don't know the velocity of either object after the collision. So, when objects collide and they don't stick together, their relative motion after the collision is described by the coefficient of restitution. Coefficient of restitution, it's symbolized with a script letter E, and the definition of the coefficient of restitution is minus V2x final, actually I should say the coefficient of restitution is defined as minus the quantity V2x final minus V1x final divided by the quantity V2x initial minus V1x initial. What that is telling us is that the velocity with which the objects are going away from each other afterwards divided by the velocity with which they approached each other initially is equal to this quantity called the coefficient of restitution. If the coefficient of restitution is exactly 1, then that's something that we call a perfectly elastic collision. And what that means is that the objects recede from each other after the collision with exactly the same relative motion as they approached each other. That also means, as I'll show you in a second, that the kinetic energy, the total kinetic energy of the two objects is conserved. So no energy is lost in the collision. The other end of the spectrum is where E is equal to 0. And if E is equal to 0, taking a look at our equation, you can see that V2x final must be the same, must be equal to V1x final, so that the two objects are not moving relative to each other, they're stuck together. And that actually represents the greatest possible loss of kinetic energy in the collision. So let me show you some examples of that. Let me do a perfectly elastic collision to begin with. Let me have my x direction. I have, let's say, a 2 kilogram mass moving at 1 meter per second collides with a 1 kilogram mass at rest. That's our initial situation. And they collide. And finally, the 2 kilogram mass is moving with a different we'll call that V1x final. And we'll assume that the 1 kilogram mass is now moving with some V2x final. We'll call it, remember that this is mass 1 and mass 2. So the 2 kilogram mass is mass 1 and the 1 kilogram mass is mass 2. And this is our final situation. Let's calculate our initial kinetic energy. K initial, it's all in the 2 kilogram mass. Remember that kinetic energy is 1/2 mv squared. So that'd be 1/2 times mass of 2 times v of 1 squared, which gives us a kinetic energy of 1 joule. So we start off with 1 joule of kinetic energy. Let us first try out the case where the coefficient of restitution is equal to 1, or we have a perfectly elastic collision. A perfectly elastic collision. So, well, we still conserve momentum. So, P total x final equals P total x initial. And this is our x direction. So that says that 2 kilograms times 1, I'm sorry, let me do that the other way. This is initial and this is final. So initial and final. So initially we have 2 kilograms moving at 1 meter per second plus 0. And finally, we have 2 kilograms moving with V1 V1x final plus 1 kilogram moving with V2x final. So that says that 2 is equal to 2 V1x final plus V2x final. And what I'll do here, well, I'll just leave that for right now, because what do we have? We have an equation, we have one equation with two unknowns. So that means that we need another equation. Our other equation is going to be our coefficient of restitution equation. So I'll add over here, epsilon is equal to 1. No, not epsilon, E. E is equal to 1. So our coefficient of restitution equation is E is equal to minus V2x final minus V1x final. That's just the definition of coefficient of restitution over V2x initial minus V1x initial. E is equal to 1, so 1 is equal to minus V2x final minus V1x final divided by, well, V2x initial is 0 minus V1x initial, which is 1. And so here we have 1 is equal to negative this divided by negative 1. Well, I can cancel off these negative signs right here. And that would be 1 is equal to V2x final minus V1x final, because I have a negative divided by negative 1. Okay, so now I have two equations and two unknowns. What I will do is I will solve this equation for V2x final by adding V1x final to both sides. So I have 1 plus V1x final is equal to V2x final. And this right here is the same as V2x final. So I will take that and I will substitute it in for V2x final over here. So that gives me 2 is equal to 2 V1x final plus 1 plus V1x final again, because this right here is my V2x final. So I have a plus 1 on this side. I'll subtract 1 from both sides. That says 2 minus 1. And here I have 2 Vx final plus Vx final. So I have another Vx final equals 3 V, and that's V1x final. Which tells me that 2 minus 1 is 1. I'll divide both sides by 3. 1 over 3 is equal to V1x final. So V1x final is 1/3 of a meter per second. It's equal to 1/3 of a meter per second for our first object, our 2 kilogram mass. Now that we know this, we can substitute it back in over here to calculate V2x final. So 1 plus 1/3 is equal to V2x final, or V2x final is 1 1/3. I'm going to write that as 1.33 is equal to V2 2x final. So V2x final is 1. Actually, I'm going to go ahead and write it as 1 1/3. Okay, V2x final is 1 1/3. So, using our coefficient of restitution equation, we were able to calculate the velocities of both objects after the collision. Well, actually, I should say, using our conservation of momentum equation and our coefficient of restitution equation, which gives us two equations, we were able to calculate two unknowns, which are the two velocities after the collision. Now, I said that in a perfectly elastic collision, we conserve kinetic energy, meaning no kinetic energy is lost. We had 1 joule of kinetic energy before. Let's see how much kinetic energy we have afterwards. So our final kinetic energy, K final, is 1/2 mv squared for this block. 1/2 mass of 2 times 1/3 squared plus 1/2 of this mass, which is 1, times its v squared, which is 1 1/3 squared. And let's see what we get from that. I have 1/2 times 2 times 1/3 squared plus 1/2 times 1 kilogram times 1 1/3 squared. And, as I was expecting, I get 1 joule of energy. So, we had a 2 kilogram mass moving at 1 meter per second collide with a 1 kilogram mass that was at rest. We used our conservation of momentum and the idea that we had a perfectly elastic collision, which gave us our coefficient of restitution of 1, and we used our coefficient of restitution equation to calculate the final speeds after the collision, which gave us a velocity of 1/3 of a meter per second for the first mass, 1 1/3 meter per second for the second mass, and then we showed that not only could we calculate both of these velocities, but since we had a perfectly elastic collision, the total kinetic energy was conserved. So no kinetic energy was lost in this collision. That's not going to be the case with a perfectly inelastic collision. What we're going to see, or with any other collision for that matter, as long as E is not equal to 1, then the kinetic energy will not be conserved. Let's do another example of that. So let's use the same situation. We have mass 1, which is 2 kilograms, and it's moving at 1 meter per second, collides with mass 2, which has a mass of 1, and it's at rest, and it collides. So this is our initial situation. And we had a kinetic energy of 1 joule we calculated. And this time we're going to have a perfectly inelastic collision. E is equal to 0. Perfectly inelastic collision. which means I'll go ahead and write my E equation over here. E is equal to minus V2x final minus V1x final divided by V2x initial minus V1x initial. And if E is equal to 0, then the only way that that can happen is if V2x final is equal to V1x final, or these two objects have the same V final. So we know that they are stuck together and they're moving with Vx final, whatever it is. So this tells us that V2x final minus V1x final is equal to 0, or V1x final equals V2x final. So now, when we use our conservation of momentum, P total initial equals P total final, we get 2 times 1 plus 0, 2 times 1 plus 0, equals 3 times Vx final. 2 times 1 is 2. We'll divide by 3. That tells us that 2/3 is Vx final, or our object is moving finally with a speed of 2/3 of a meter per second. And we can calculate K final. It is 1/2 of 3 kilograms now. 2 plus 1 is 3 kilograms times the speed of 2/3 of a meter per second squared gives us a final kinetic energy of 1/2 times 3 meters per second, times 3 kilograms, 1/2 times 3 kilograms times 2/3 of a meter per second squared gives us 0.667 joules. So what has happened is that in this collision, we have lost energy. We've lost 1/3 of a joule of kinetic energy. Where did that energy go? Well, when the objects stuck together, they deformed. It took work to deform these two objects. Some of the energy went into heat. Whenever things collide, they get hot. Or went into sound or other forms of energy. So in a perfectly inelastic collision, we lose the maximum amount of energy possible. If we have an E that's somewhere between 0 and 1, we lose a amount of kinetic energy that's somewhere between a perfectly elastic collision and a perfectly inelastic collision. So, this gives us another tool that we can use when we are dealing with collisions. And we'll talk more about this next time. Until then, think physics.